and the difference between sharding and replication. Okay, fine. I mean, you can read that. In replication, the entire data set, if you have 1 GB data, the entire 1 GB data will be on multiple other servers. So that if one server crashes, the other server takes up. Within sharding, you only take certain pieces of this 1 GB data. Out of 1 GB data, say 400 MB will be here. Another 600 MB will be here. Okay, not the entire 1 GB. That's called as sharding, right? And it maintains something called as shards, okay, or some kind of shard keys, which says that out of 1 GB, 400 MB file I'm storing in different computers or servers, 600 MB I'm storing in different other computers. As opposed to copying everything, I'm copying only portions of that. If this goes down or if this is very busy, I'll pick it from here. If accessing this part becomes difficult and if this server becomes busy, I'll access it from another server. Okay, that's the difference between compression and sharding. Okay. Now, these are just a few hyperparameters, not at all complete. These are just a few. Number of estimators is number of trees, number of decision trees that you want to run. Learning rate, the default value is 0.3. It is also called as eta value, represented like this. More about this we'll learn when we get into neural network algorithm. So, as opposed to your gradient boosting, in extreme gradient boosting, different iterations are given different weights. Okay. In gradient, okay, in ADA boost, what happened? Was equal weightage given? No. Different weightage was given for different iterations. In gradient boosting, what happened? Constant. In extreme gradient boosting, what it does is, it understands that once you build your algorithm, when you take the errors and using errors when you build another algorithm, you'll get again errors. Okay. Now, when you build one model and when you get the residuals out of that, maybe residuals will have some information. So to capture that information, what are we doing? We are once again building the model. After we build the model, again, you'll get residuals. Do you think the residuals here will have less information than the residuals here? Obviously, distillation. From residuals, you're taking the information. Again, when you get the residuals, obviously there'll be less information. Again, you take that less information, build a model. Again, when you get residuals, will the information be least here? Yes, in comparison to these two, it will be least. So the amount of information contained in residuals from the first model to second model to third model to fourth model will be decreasing. So what extreme gradient boosting does is it will say that, okay, let me also keep adjusting the learning rate value so that I shrink the weightage given. In every round, in every iteration, the weightage given to the algorithm will be reducing because the information is less. Maximum depth anyways we are aware of, and we have something called as gamma value. Okay. Gamma is alias for minimum split loss. If I'm splitting a tree, I will continue splitting as long as the error value keeps on decreasing. Okay. So you put a condition saying that if I say 0.3, for example, what do you mean? At least if there is 0.3 reduction, 0.3% reduction in the error, only then I will split. If the error is not reducing, if the reduction is error in the error is only 0.1%, then I will not even continue further. I'll not split. Only if the minimum error reduction is 30%, only then I will split the tree further. Otherwise, what will happen? You'll continue building your tree. You'll be making your model more and more complicated for least benefit. When you're splitting it, when you're taking that additional step, when you're including that additional rule in your algorithm, it should give you improvement, significant improvement. Otherwise, why should you do that? Okay. Then you have minimum child weight. Okay. What is the minimum sum of weights required for a node to split? Okay. Then you have weights which are given right here. The weightage that is given to each and every tree. What is the minimum sum of weights required for a node to split? So here, if this is the node, you will assign weightage. Okay. That weightage should be minimum some number for you to proceed further with the split. Okay. Then you have subsamples. You have column samples, column sample by tree, by level, by node, scale positive weight, maximum delta step, lambda, alpha, missing, so on and so forth. When we get into regression techniques, we will talk about something called as lasso regression. Are you done with this? Lasso and ridge regression? Not sure. So we'll talk about lasso and ridge regression. Those are this L1 and L2. Okay. And then just go through these hyperparameters whenever you find time. Okay. There's one big math derivation which is available. While I'm aware of that, I really don't know whether I should confuse you or not. Okay, let me just write it here. So the objective function here of t is equal to minus 1 by 2 sigma j equal to 1 until t gj square divided by hj plus lambda plus gamma. I can derive it very easily, but I would not do that. This in itself, I'm sure you're getting a sense on how this is looking like, right? So do reach out to me if you feel that you want to know the derivation. Okay, you can just message me. I'll do the derivation on a paper, take a screenshot and share it with you. But otherwise, brush it aside.